So here's a design that I will work with in configuring the ASPRs as stated earlier. In this design, the aim for this particular config is to establish reachability between the LAN segment on the remote site to the LAN segment on the campus site. But before then, I will show you some basic configurations that have been done on R12, R13 and R14 respectively. Here on R12, these are the IP addresses that are configured. And so we have the 192.1.20, the 12 network as well. Those are the two prefixes. Already we have BGP configured, but we are not learning anything yet from R11 in this case. Same as R13, we have a configuration of BGP, which is on that segment that is connected to R3, and we can see also that there are some prefixes that are learned already. There is only one prefix which was advertised by R3, and that is the one that we have directly connected. And these are the IP addresses which are directly connected to R13. While on R14, we have BGP also learned. Remember, R14 is meant to be a backup for that campus site. That is why we have a pairing between R13 and 14 on the 192.168 segment, while the 14.001 is R4 in this case. And we can see there are three routes that are only coming from that end, because this is actually a backup circuit. These are the IP addresses configured directly on R14. Currently, there is no reachability between R14, or as you may say, between the campus site and the remote. There is no connectivity yet because the reachability has not been established by routing. So the same thing is happening on R13. We can't reach the remote site when we source it from the LAN. That was not successful either on R14. Similarly, on R12, we cannot reach any of the LAN segments that are located in the campus site when we source it from the LAN IP on R12. And that is the essence of this configuration, for us to achieve this and confirm all the paths that are participating in the routing. So as we see here, none of the IPs are reachable. On the ASPR, we will configure both ASPR. In this case, R4 and R9 are acting as backup, while R1 and R10 are the primary. And R2 is a route reflector for those routers in service provider 1. As we see here, there is already pairing, which is part of our assumptions earlier, as I stated. And there are also some prefixes that are already learned from the route reflector, which were sourced from the PE. So there are only 8 prefixes, and you will see that these prefixes are coming from PE, which is for that VRF. We are seeing it on ASPR because we have a VRF in that particular segment, and this was configured in my first video. So we'll go by the configuration guide, first we have to disable the automatic route filtering as stated. As soon as you have that, you can also check and verify if there is any changes. Nothing yet. Then the next thing we do is to configure the multi-protocol MP-BGP. Remember, in option B, we do not need to enable LDP or IGP or VRF on the inter-AS link. So all we just need to do is configure the MP-BGP between the ASPRs on both service provider networks. As soon as we have this configured on R1, we can copy these configs and modify it on a notepad and apply it on R10 in order to reduce our time. Just highlight, copy that on a notepad, go to R10 and apply those configs in order for you to establish the MP-BGP. So on R10, there are no other configurations than the IP addresses that we have, and that is for the inter-AS link. Currently, there is no peering between R10 and R1 on that inter-AS link. So we paste the already modified configuration, wait just for a few seconds, and we can see the establishment of the MP-BGP. And remember, as soon as you do this, automatically MPLS BGP forwarding is enabled on the inter-AS link in order to allow BGP to forward MPLS based packets over that link. And remember, you also have to disable the ARF, which is a very important feature when deploying inter-AS MPLS VPN. Now we have the peering established, but there is no prefix coming yet. Similarly, on R1, you will see the automatic enablement of that MPLS BGP forwarding. Currently, there is nothing coming over the inter-AS link. So we have 0 prefixes coming over that link. Nothing is happening yet. Remember to disable the ARF also on R10. And verify again. So we have the peering on the MP-BGP formed, but there are no prefixes learnt yet. Similarly on R1, there are no prefixes also learnt over the inter-AS link yet. But we can see there are 8 prefixes coming from the route reflector. And in order to achieve this exchange of routes, we have to check on the route reflector if there is any form of filtering on the route reflector. Here we can see that there are some prefixes on that VRF because they were configured already on the R1 in my previous video. But in this case, the route reflector needs to disable the ARF feature in order for R1 to learn about the VRF that was dedicated for this remote on the campus site. And we see here the route reflector has a VRF which it is not giving out. As we see, 15,64717 has not been given to R1, but because we have now disabled that and we refresh the routes, we will be able to see this on the R1, and that is exactly what's just happened. So if you are deploying this solution with a route reflector, it is important for you to consider this option in order to avoid any form of unplanned filtering. Now we can verify on R10 if we are getting those routes now, and you can see that we have 7 prefixes coming over the inter-AS link, and they are coming from that VRF and also sourced from R10. That VRF is dedicated on R3, which is the PE to that campus site, and that is exactly the one we have received on R1, which has also been given to R10 in this case. And that is it on the first two segments that we have to configure. We do the same on R4. We have to just modify the configuration and apply same on R9 in order to pair between both routers that are acting in this case as our ASBR of the two service provider networks. So after you must have completed the configuration of R9, you can copy and then paste on R9 in order to form the adjacency of the MP-BGP. The same thing is happening in this case, which is the pairing that has just happened between R9 and R4. And here we are seeing 16 prefixes because R4 also has a copy of the other VRF, which is adding up to what we have for the intended VRF. As you see that we have 15,604 table and 15,649 table as well. So all of these prefixes are coming over the inter-AS link between R4 and R9. These are exactly the copies of the prefixes that are coming from R3, as we can see. R11 is acting as a route reflector in this case. We are expected to be seeing these prefixes also, and as we see, there are two prefixes coming from R12 towards the route reflector, which is also the PE in this case. And these are the routing table that are being learned from R9 in this case, and that is the one coming from R12. But there is something that we notice: the prefixes that are learned from R9 and R10 are not seen as best path, which is why we only have asterisk before those prefixes in the BGP table in the case of 15,064,717 and 15,064,923. And that is exactly the purpose of the Redistribute-Connected method in deploying inter-AS MPLS VPN. So, to overcome this, because typically what is happening in this case is because the router R11 does not have reachability to the next hop addresses for each of those prefixes, which is a basic requirement of BGP that has to do with reachability of the next hop before a prefix is considered best or even reachable. And as you see in this case, 49.0.0.0 is not reachable from this router. The same thing applies to 110.0 network, which is not also reachable from this router. And that is the essence of redistributing the inter-AS link prefixes into the local IGP. And in this case, we have to do that on R9 and R10 by redistributing connected into IS-IS network. Similar to what we had before, we have to also consider disabling the auto route filtering option or feature on the route reflector. So we go to the route reflector and disable the ARF feature in order to allow the prefixes coming from the R12 remote site to be able to reach R10 and R9. As you see now, we have these prefixes already installed in the MP-BGP global table on R9 and R10 respectively. Now we are learning the two prefixes that are being advertised by R12 on R9 and R10. So R10 also now has received those prefixes from R11 and also a copy of the table from R1. On R11, the table looks exactly like this. Now you notice these prefixes are learned, but they are not selected as best path because there are no reachability to the next stop address. And that is why we have to redistribute connected into our local IGP. We'll have to leave the third point and just go to the redistribute connected, after which we'll come back to implement the rewrite target. So R9 needs to redistribute the inter-AS link, which is directly connected, into its local IGP, which in this case is IS-IS. And so in order to prevent the distribution of unintended locally connected prefixes, we have to use the route map and match that interface. And we can call on this route map in the redistribution process as seen in this example. So we specify a metric of 90. I'm not ready to change any default setting on the redistribution by considering wild style of metric in ISI, so I'm downgrading that to 20. So we can just leave that as is. And then we can verify reachability now is established. As we can see, those routes have been installed in the routing table, and we expect that this will change the status. Now you can see the greater than sign, which means that is the best path because the next up address is now reachable. And for you to see a comparison between both sources, we can do a specific lookup, let's say 14 for instance. When you pick that and you check it, you'll see two routes are available. One is the best, and let me clear that screen. You can see it's coming from the best path is the number 1, and it's coming from 9 with a metric of 94, and the other is coming from R10, but inaccessible. And that is the reason why it is not able to be considered in the BGP table. And in order to overcome this, we need to redistribute connected on R10 into the IS-IS. Just similar action that was taken on R9 needs to be done. You use your route map to match that interface specifically. Mind you, the route map can be named according to your own style of convention. And then you can call on that route map and attach your metrics. Remember to specify the level that you are redistributing into when using ISI. Okay, and we can verify again. So checking this out, it's still taking some time, and when you check that out, you can see that it has now been able to see that it is reachable, which now has a metric of 84 through R10, and it is considered the best path for that VRF. It's also best path, but there are two different VRFs. If you look at the route target, in this case, there are two different route targets. We will address that later on as we go in this section. So the network now has converged and has decided to pick the best path based on the VRFs. So on R12, we are not learning these prefixes yet, simply because there is no match between the VRF or the route tag that was configured on R11 and the one that is coming from the other end, which is from the service provider 1. And that is the essence of having to rewrite the VRF. As you see, on R11 we have a route target of 54230, which is not matching the 15,000 route target that was coming from the remote AS, and that needs to be addressed. So let me show you one more time. So we are getting 15,064,717 from remote AS, but the local AS is using 54230, which is different, and that is why it is being filtered out and not getting to R12. In order to solve this problem, we can rewrite the route target on the ASBRs. We can either rewrite or consider an importation. Like I mentioned earlier, we don't need to do that importation if we are rewriting on the ASBR, and that is why we can just go ahead to configure this ASBR to rewrite any route target that is coming using the extended community list. So we match based on what is coming, which is 15,064,717, and then we use a route map to match based on this entry, and then we can use the set command to delete this particular route target, while we also use another set statement to rewrite what we want to write on these particular prefixes when they arrive. So we use the local RT to replace the one we deleted that was coming from the remote end. That is exactly the approach of rewriting. And because this is going to act as a backup, we can use other attributes like the local preference, in this case, just a simple example to reduce the preference. After which, we can then verify and apply this route map to inbound traffic as they come from R4. So we just do that and apply in the inbound direction. And then we do a route refresh, and we can then go to R11 to verify if we are seeing this. We can check this also on R9, and also on R12 we can see that now we are getting 7 prefixes coming, which we were getting before. And we can go to R11 in this case and check again if we have any change in the copy of the table we have currently. At the moment, it doesn't look like there is a huge change, but that prefix coming from the routing table there is no longer in our copy of this table, which means the route map already filtered those out. There were no matches, and that is why it was taken out. On R12, we are not seeing so much yet because it's still waiting to fully converge. So we replicate same on R10. Remember, we look out for a particular route target. We permit it in our extended community list, and then we match based on the route target that is coming from the remote AS. We use a route map in order to match and delete and reset also, which is the rewrite operation actually. So we match based on the extended community list. We set to delete, then we set to rewrite also. As soon as we have this done on the route map, We verify that route map and apply it also to the MP-BGP peer. In order to have this activated, that is the rewrite operation of route map, we apply this inbound. So any prefix that is received from R1, in this case, we'll have to rewrite the route target, and we can refresh the route. Remember, it's only a soft refresh in this case. So we are learning the prefixes. We can go back to R11 and re-verify. Now you see that we have more routes that has been injected into our routing table for a specific VRF, which is local to service provider 3 in this case. And so we check also on R12 that those prefixes are now being learned. Reason is because R10 is our preferred path. And so we are getting these prefixes already. Similar thing has to happen on R1 and R4 for service provider 1. But before then, let's just check what we see. So in this case, we have to rewrite these route targets that are coming from the other end, and also check R3. These are the local route targets, but we are not learning the one that is coming from the other end. So we have to also rewrite on this side. We permit what is coming from the remote end, which is 54,000 series, and then we use a route map just similar to what we did in the previous service provider ASPR. We match that extended community, then we change the route target to the local route target in our case. We are using the local preference to influence the traffic flow, so we are preferring R1 and R10 as our primary, which is why we have a higher local preference. After this, you can apply it to the MP-BGP peer and apply this in the inbound direction. Then you can refresh your routes and then verify as well. And we also need to do the Redistribute-Connected on R1 and R4 respectively. Remember, use the route map to match the exact interface which you are willing to redistribute into your local IGP. In this case, we are running OSPF, and R1 is a preferred path, so I'm using the metric type 1 and applying it to this route map. So that should take care of that issue of reachability to the next stop. The same thing on R4. We call on the route map. We match the local interface of the inter-AS link. Then we apply it to the redistribution. In this case, because R4 is going to act as a backup path, we are using the metric type 2 just to have a preferred path between R1 and R4 respectively. Call on the route map and apply that as well. Then we can go back and verify on R2 being our route reflector to see that we are learning these prefixes already. That is injected into the routing table, and so we can go ahead to rewrite route targets. That is the remote route target. We apply that to match. Then we go on the route map to rewrite this remote route target to our local preferred route target. So remember, this is not a mandatory step or method. It's only an option. Remember to always use the additive so that when these routes are propagated, they are propagated alongside. The route target is propagated together as it goes to other routers. After this, you can then apply it to the MP-BGP, which is to allow all these prefixes to learn the prefix alongside with the route target's rewrite. I'm specifying a lower preference here because that is a backup path. After that, you can then apply it in inbound direction. Then you can refresh and let's verify. So we have a routing table for different VRFs, but in this case we are learning already things that are coming from service provider 3, and as you can see in this case we have our local preferences as specified, and the next up addresses are also reachable. On R3 we are learning these prefixes from the route reflector and also from R3. Also on the route reflector we are seeing these prefixes and all the copies of the routing tables as well. On R3, looking at a specific VRF, AFENT in this case is dedicated to remote site, and you can see that we are learning prefixes that are already coming from the remote site. But on the other hand, the NAM does not have these prefixes. That is because we have the rewrite configuration working as expected. So in this case, there is no worries of any form of leaks that could happen between those VRFs because we already have a method in which traffic is being segregated by the route target. Now, if you focus more on a specific prefix coming from the remote end, you would see that it's been imported from a table which is global. That is the MP-BGP global table. It is being injected into the local VRF. And checking also on R11 for the same prefix coming from SP1, you would see that we are learning specifically those prefixes that are coming from the campus site, which is an acknowledgement that we have this route fully exchanged. And the same thing on R12, we would see that R12 now is already learning these prefixes. So at this time, we can verify if R12 is able to reach the campus site. And that is the next thing that we will have to check using the ping tests and sourcing it from the local IP address. We have reachability, and if you run some trace as well, you would see that we are taking a particular path through R10 to get to the campus site. I'll run that again. So it's going through R10 to get to R1, and then to the route reflector and to the PE, and of course to the campus site. So the reachability is being established already. And if you look backwards again in the reverse direction from campus to remote on R13, we have reachability, and the path is through the route reflector to R1 to R10 to R11, and then to the remote, which is exactly the path that we want it to take. Similar thing on R14 in this case. Don't worry about the timeout, it's just because it's the first time it's happening. So there are lots of other background things that happen, like the ARP and of course other routing processes as well. So the path here is taking R13 being the primary path, and similar to what happened before, the route reflector R1 and of course the R10. R14 has to go through R13 to go out of the campus site, and that is exactly what is going on here. So R13 must always be the primary, which is what we have going through R3, R2, R1, R10, R11 and to the remote, exactly as we wanted it to happen. We have achieved this particular aim, and it appears that traffic is flowing through the primary path. But what about if there was a failure on the primary path? Then we will need to see how the network will fail over traffic to the secondary path. So let us shut it down on both ends and see how the traffic will flow in this case. I'm shutting down the interface also on R1 for the primary inter-AS link, and we can run again on the trace routes and the ping test as well, just to see how traffic will flow. So first thing is that you see that the next stop has changed, as well as the local preference, which is showing us that traffic already has been switched to the backup inter-AS path. That's exactly where it is, and it is why it is important to always have a backup inter-AS path, especially between service providers, in order to avoid any single point of failure. So just ignore the high latencies that you're seeing. It's due to the background processes running. We are running a trace route again from R12 to the campus, and you see it's taking a shorter path. Now, depending on what your design looks like and what you stand to achieve, you have to use the BGP metrics, the IGP metrics as well, to tweak the direction of your traffic flow. Your traffic engineering skills needs to come into place depending on what you're willing to achieve. And you can see also from R14, traffic is flowing through that backup path, which is symmetric. So we have the symmetric routing also between R13 and R12, which is the campus to the remote. Now we can activate our primary path and just normalize the network as is supposed to be. That is it, and now we are able to achieve the reachability between the remote through the primary path to the campus end. So we have some servers behind the routers in the campus site which are able to reach the remote site depending on the status of any of those links between the service provider network. And of course, rewrite route target is a very useful tool which reduces your configuration on the PEs in order for you to get traffic to be properly routed. You don't need to start doing importation of VRFs into VRFs. All you just need to do is rewrite on the ASBR, and sometimes you may decide to rewrite on the route reflector. It all depends on what your constraints are. So with this config, we are able to achieve the aim of this section, which is to create reachability between the campus site and the remote site over the inter-AS links using a Redistribute-Connected option of the inter-AS MPLS VPN option B. So here are the benefits and the drawbacks of this method, which is also still similar to the previous video which I had. You can check the link below in the description section for the previous videos I've made, particularly on this topic. And in conclusion, we can see that option B is less secure when you compare it to option A. But as I've always said, your design option is always subject to the business goal among other design factors. In order for you to select any of these options and methods, there is need for a proper analysis of your business goal before choosing the most appropriate design option. Also, remember that the route target can be used depending on what you choose between importing VRFs into one another or just having to rewrite at the ASBR level in order to get your routing properly done based on the route targets that are rewritten. This is the end of this video. I hope that you found this section helpful. Please give a like, share, subscribe, and ask questions if you have any in the comment section. I'll be happy to respond to you. Until I come your way again. Thank you. Bye for now.